Today we have an invited speaker. I want to tell you a little bit about him before we get started. Mr. Haywood Satz has been a principal technical staff member in the aerospace industry full-time and adjunct faculty at UMass Lowell and Polytechnic of Brooklyn, senior grade life member of IEEE, and most recently has joined the Physics and Engineering Department at Eastern National College. Woody has modeled the physical systems of aircraft and space vehicles, flight control, radio inertial navigation, and the radar detection and orbit determination of space objects. His background and experience includes the analysis of feedback control stability and the determination of statistical filtering convergence. Mr. Satz's history also includes scientific consultation to industry, meaning a grant from NASA, the Small Business Association, to the research on global positioning system, navigation, and altitude determination of orbiting spacecraft. He was cited by NASA for an innovative approach to phase and degree resolution in the design of GPS altitude determination. Mr. Haywood Satz received the Bachelor of Science degree in Electrical Engineering from SUNY and Master of Science degree in Electrical Engineering from Brooklyn Polytechnic, along with several years of graduate research in the application of rational matrices for linear time invariant system stability. So, without any further ado, let's welcome Haywood Satz.
Thanks, Pierre. When Professor Cornelly invited me, I asked him what I should talk about, and he said I should talk about it in a half hour. So, orbit determination of space objects. Where this comes from, what I like to show is that in the work that I've done in industry, particularly trying to determine the motion of space objects and track them with radar, I've developed algorithms that would make the statistically best guess as to what the orbit was. Okay. Now the orbit, if we get a successful estimate of the two vectors, position and velocity, any place in the orbit, that determines the entire orbit. Those 6 numbers, 3 position components, 3 velocity components, determines an orbit. There is another determination, another identification of the orbit, the Kepler parameters. In this picture here, at the orbit plane, there's the object, and it's going up and around. And so this point is the ascending node, and the angle from it, these are inertial axes. That's the Earth's spin axis, pretty much constant in space, and this other direction towards the vernal equinox. The 6 Kepler parameters that identify an orbit. A is the semi-major axis of the ellipse. E is the eccentricity, how much the ellipse differs from a circle. I is the inclination of the orbit plane relative to the polar, the Earth's spin. So there's an inclination vector. The angle from the polar axis to that vector would be this angle I. And then uppercase omega is the ascending node. It's the angle measured to that. Lowercase omega is the angle, the argument of perigee. So measured from here up to the closest point on the ellipse. And then finally, nu is the angle to the position of the object in the orbit plane. We end up with these are a number of different sample paths of error that result from the algorithm straining to do its best. The algorithm also, one of the details of developing that algorithm is that it needs for itself to compute an estimate of the error, a statistical estimate of the error environment that it's in.